Ladies and gentlemen, we are also live on our official YouTube channel at ITD IIUM Kuantan. A very warm welcome to all the viewers on YouTube. We'll be sharing the attendance and the program book links in the chat box. Kindly make sure to fill in the attendance form at 10 a.m. Please also share the YouTube link to those who are unable to join us physically today. We welcome everyone to tune in. Thank you to those who have just arrived. Please kindly fill the seats at the front. The QR codes for attendance and the program book are displayed on the sides of the hall. You can register when it is open at 10 a.m. Thank you to everyone who has arrived. Inshallah, we will start at 9:30. Please kindly set your phones to silent mode so that we will not interrupt the session. Ladies and gentlemen, let us watch and listen to the public safety announcement.
May we have your attention, please? This is a public safety announcement. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to International Islamic University Malaysia, Kuantan campus. You are now in the banquet hall. Upon the sound of a fire alarm or when evacuation order has been issued, please evacuate the building immediately. Emergency situations can be triggered by the presence of potential hazards such as fire and natural disaster. This hall has 7 main emergency exits. Please take notes on emergency evacuation routes, locations of exit doors and staircases. Exit signs will remain illuminated at all time. Please take a moment to locate the nearest exit to you. During evacuation process, please remain calm and walk to the nearest exit according to predetermined evacuation routes. For faster and safer evacuation process, please refrain from talking and running. Once you are outside the building, please proceed to the nearest assembly point and wait for further instruction. Thank you for your attention. This message is brought to you by IIUM Safety and Health Committee. Safety is as simple as A, B, C. Always be careful.
Thank you very much. Ladies and gentlemen, I would like to inform once again a housekeeping announcement. Please set your phones to silent mode so that we will not interrupt the session, inshallah. Please kindly fill the seats at the front. The QR codes for attendance and the program book are displayed on the sides of the hall. At 10 a.m., you can register using IATN QR code for attendance. Thank you. Bismillahirrahmanirrahim. Ladies and gentlemen, please rise. Announcing the arrival of our guests and VIPs. Please kindly remain standing for the national anthem Negaraku, followed by the IIUM anthem leading the way. Ladies and gentlemen, you may all take your seats. Assalamualaikum warahmatullahi wabarakatuh and good morning. Professor Dr. Samsul bin Rahman, member of the IIUM Board of Governors, Associate Professor Dr. Muhammad Arifin bin Kadri, Deputy Campus Director, Professor Dr. Ahmad Aidil Arafat bin Zulkarnain, Dean Kuliah of Allied Health Sciences, Professor Dr. Muhammad Zulfaizal bin Che Azmin, Head of Research and Innovation, Kuliah of Allied Health Sciences, Dr. Iqbal bin Jamaluddin, Head, Department of Diagnostic Imaging and Radiotherapy, Professor Dr. Syed INAYATULLAH SHAH, Distinguished Speaker, Deans, Directors, Deputy Deans, Heads of Departments, Professors, Associate Professors, Doctors, Sir, Madam, Brothers and Sisters. And also not to forget to all our viewers who are watching live on YouTube, ITD IIUM Kuantan. Ladies and gentlemen, to invoke the blessings of Allah, please allow me to invite Dr. Iqbal bin Jamaluddin, Head, Department of Diagnostic Imaging and Radiotherapy, to recite the opening dua. Please welcome.
Assalamualaikum warahmatullahi wabarakatuh. Al-Fatihah. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdan yuafi ni'amahu wa kafi'u mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhikal karim wa azim sultanik. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Ya Allah, we begin this gathering with gratitude in our hearts, acknowledging your boundless mercy and wisdom. You are the source of all knowledge and understanding, and it is through your divine guidance that we are able to come together today in pursuit of knowledge. Ya Allah, please send your blessing upon our esteemed speaker, Professor Dr. Syed INAYATULLAH SHAH. Grant him your guidance and wisdom as he shares his insight with us today. Bless him with clarity of thought and expression so that his words may be a source of inspiration, understanding, and reflection for all of us present here. Ya Allah, we ask you to bless us with the ability to truly benefit from the knowledge that will be shared. Open our hearts and minds, let the wisdom imparted not only enrich our intellectual understanding, but also guide our actions in ways that benefit our communities, our nation, and the Ummah at large. Ya Allah, we seek your mercy in every endeavor we undertake, especially in our pursuit of knowledge. Grant us the strength to seek knowledge with humility, the wisdom to apply it for the good of all, and the patience to continue striving in our academic and personal journey. Ya Allah, we seek for your forgiveness for any shortcomings, and we ask for your mercy and blessing in all that we do. Grant us success in this life and the hereafter, and keep us steadfast on the path of knowledge and righteousness. Allahumma inna nas'aluka ilman nafi'a wa rizqan tayyiba wa amalan mutakabbala. Allahumma ja'alna haza jam'an marhuma wa tafarruqana min ba'dihi tafarruqan ma'suma. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wa barik wa sallim walhamdulillahi rabbil alamin.
Amin ya rabbal alamin. Syukran Dr. Iqbal. Melati kuntum tumbuh melata, sayang merbah di pohon cemara. Assalamualaikum, mulanya kata, saya sembah pembuka bicara. Ladies and gentlemen, I am Dr. Nur Nadiah binti Muhammad Rais, and today I will be your master of ceremony. First and foremost, on behalf of the organizing committee, I would like to extend our warm welcome to all of you for being here at today's event. Today, on the 31st of July 2025 and the 6th of Safar 1447 Hijrah Allah has enabled us to gather here to witness the 5th Professorial Lecture in 2025 by our professor from IIUM Kuantan campus. In the framework of Tawhidic knowledge, which emphasizes the unity of knowledge as stemming from the oneness of Allah, such a lecture is a means which emphasizes the unity, the divine trust and amanah of knowledge. This morning, we will be celebrating the first appointed professor from the Department of Diagnostic Imaging and Radiotherapy, Professor Dr. Syed INAYATULLAH SHAH, who will be delivering his professorial lecture in this honorable hall. Ladies and gentlemen, I would now like to invite Professor Dr. Ahmad Aidil Arafat bin Zulkarnain, Dean, Kull of Allied Health Sciences, to deliver the welcoming remarks. Please welcome.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajmain. Assalamualaikum warahmatullahi wabarakatuh and very good morning. Professor Dr. Samsul bin Rahman, member of the IIUM Board of Governors, Associate Prof. Dr. Muhammad Arifin bin Kadri, Deputy Campus Director, the Deputy Deans of the Kull of Allied Sciences, our new Professor, Prof. Dr. Muhammad bin Ibrahim, Deputy Dean of the Postgraduate and Research and Innovation, Associate Prof. Dr. Saiful Ali Jamaluddin, the Deputy Deans of the Academy and Internationalization, Professor Dr. Muhammad Zul Faizal bin Cik Azmin, the Head of Research and Innovation, Assistant Prof. Dr. Iqbal bin Jamaluddin, the Head Department of Diagnostic Imaging and Radiotherapy, Professor Dr. Syed INAYATULLAH SHAH, the distinguished speaker for today's event, the Head of Departments, the Professor, Associate Professor, Dr. Sir, Madam, Brother and Sister. Alhamdulillah, today we gather in this hall to either physically or virtually to actually celebrate our distinguished speaker. And it gives me great pleasure to actually welcome everybody to the 5th Professorial Lecture of 2025, and it will be the second one for the Kull of Allied Health Sciences. And today's the lecture will be delivered by our distinguished colleague, Professor Dr. Syed INAYATULLAH SHAH from the Departments of Diagnostic Imaging and Radiotherapy. So on behalf of the Kuliah, I express my sincere gratitude to everyone for being with us to honor and celebrate the significant academic achievement and dedicated service of Professor Dr. Syed. And throughout his time at IUM, Prof. Syed has not only demonstrated expertise in the medical physics, he also has been a very committed educator and mentor respected by colleagues and students alike. And today's event holds special meaning as it marks Professor Syed's final official day with the university after more than 15 years of dedicated service since joining IIUM in July 2009. And this occasion provides us with the opportunity to express our deepest appreciation for his academic excellence, commitment and invaluable contribution, which have significantly enriched our university community and the broader field of healthcare sciences. The lecture today entitled Medical Physics and Imaging, the Synergy of Science and Technology in Modern Healthcare, addresses important developments and practical implications in the field of medical imaging and radiotherapy. Professor Syed's scholarly contribution, particularly in nuclear medicine, radiation dosimetry and radiation protection, have significantly advanced the safety, accuracy and effectiveness of these elements in the critical healthcare technologies. At the Kull of Allied Health Sciences, our mission remains to nurture ethical, knowledgeable and skilled healthcare professionals guided by Islamic value So today's lecture is one of the example. This mission by highlighting how scientific innovation and human compassion can effectively converge to improve patient care. And Professor Syed career stand as a clear example of this integrated approach to research and services. And I wish to extend my heartfelt appreciation to the organizing committee for their dedicated effort in ensuring the success of this event. And special thanks also goes to the campus director, the members of the Department of Diagnostic Imaging and Radiotherapy, academic support services, the office of the campus director, and the Office for Communication Advocacy and Promotion, or CAP, at IUM campus for their excellent collaboration and support. I hope today's lecture will inspire all the academic staff of the Kuliah of Allied Health Sciences to strive for excellence, just as our distinguished speaker, Prof. Syed. And Prof. Syed, as I mentioned, has demonstrated through his dedication and tireless effort in the field of the nuclear imaging, and his remarkable commitment serve as a shining example for all of us at the Kuliah of Allied Health Sciences to emulate in our role as the Murabi, educator and mentors, and dedicated to Prof. Syed academic and the personal excellence. And let us take a moment today to pray for Professor Dr. Syed INAYATULLAH SHAH. May Allah Subhanahu wa Ta'ala grant him continued help, strength and success in his future endeavor, allowing him to further contribute to the society and the pursuit of knowledge. And it is my hope that this lecture will encourage insightful discussion and inspire fruitful collaboration. And once again, congratulations to Professor Syed INAYATULLAH SHAH on reaching this important milestone. We eagerly look forward to listen to his lecture. With that, I warmly welcome all of you again to the 5th Professorial Lecture of 2025 and the second one for the Kuliah. And with that, wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Dr. Ahmad Aidil Arafat. Distinguished guests, brothers and sisters, we are very close now to our main event. But before that, I would like to invite Professor Dr. Muhammad Zulfaizal bin Che Azmin, Head of Research and Innovation, Kuliah of Allied Health Sciences, to deliver a biography of our speaker for today's Professorial Lecture. Please welcome.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Professor Dr. Samsul bin Draman, member of the IIUM Board of Governors. Associate Professor Dr. Muhammad Arifin bin Kadri, Deputy Campus Director. Professor Dr. Ahmad Aidil Arafat bin Zulkarnain, Dean of the Kuliah of Allied Health Sciences. Assistant Professor Dr. Iqbal bin Jamaluddin, Head Department of Diagnostic Imaging and Radiotherapy. Professor Dr. Syed INAYATULLAH SHAH, Deans, Directors, Deputy Deans, Heads of Departments, Professors, Associate Professors, Doctors, Sir, Madam, Brothers and Sisters, Assalamu alaikum warahmatullahi ta'ala wabarakatuh. It's a great pleasure for me to introduce our speaker today. It's not just a biography, but a story that I'm going to narrate, a story of a journey of dedication, discovery and impact. Professor Dr. Syed INAYATULLAH SHAH was born on 9 February 1962 in the village of Amin Lakho, District Matiari, Sindh, Pakistan. He is the fourth among 7 siblings in a close-knit and nurturing family, where the values of hard work and education were instilled from an early age. His educational journey began at the government boys' primary school in his native village, followed by studies at the branch of government middle school Pirjando in Amin Lakho, and then at government high school Mansurah, Dipar, where he earned his middle standard certificate. He continued his secondary education at Makhdum Ghulam Haidar Government High School, Halaniu, obtaining his secondary school certificate. He pursued his secondary higher education in the pre-engineering stream at Government College Hyderabad and later at Sarwari Islamia Government Degree College, Halanu. In 1984, he graduated with a Bachelor of Science in Physics from the University of Sindh, Jamshoro, with first-class honors, securing third position. The following year, he earned a Master of Science in Physics from the same university with first-class honors and first position, laying a strong foundation for a future in academia and scientific research. With a strong aspiration to advance in the field of medical physics, he received the Central Overseas Training Award from the Ministry of Education, Government of Pakistan, which enabled him to pursue postgraduate studies in the United Kingdom. He completed his Master of Science in Medical Physics from University of Surrey, Guildford in 1991, and achieved a significant academic milestone by earning a PhD in Medical Physics from King's College London, University of London in 1996. Professor Said's journey from a modest village to renowned UK universities is a remarkable testament to his determination and scholarly excellence. His strong academic foundation and passion for science have shaped a distinguished career dedicated to education, research, and healthcare innovation. Upon returning to Pakistan, he played a pioneering role in developing the field of medical physics at the University of Sindh. His efforts were instrumental in establishing and enhancing both undergraduate and postgraduate programs. In recognition of his academic leadership and research contribution, he was promoted to Associate Professor in 1999 and to Full Professor in 2004. Seeking broader international engagement, he joined the School of Health Science at the University of Science Malaysia from 2001 to 2004. During his tenure, he was honored with the Best Lecturer Award and secured a competitive research grant, achievements, and deepened his global academic perspective and research capabilities. Prof. Said is widely recognized for his impactful and innovative research. He's published extensively in reputed national and international journals, has co-authored 2 books and on research methodologies. His work has been honored with numerous accolades, including gold, silver, and bronze medals from prestigious exhibitions such as IRI, ITEX, INEX, and MTA. His research excellence is further evidenced by a granted patent and a portfolio of completed and ongoing projects. Since July 2009, Prof. Said has been serving as a faculty member in the Department of Diagnostic Imaging and Radiotherapy, Kull of Allied Health Sciences, International Islamic University Malaysia. His ongoing commitment to academic excellence, research innovation, and international collaboration continues to advance the field of medical physics and medical imaging, making a lasting impact on healthcare and higher education. On that note, I would like to thank Prof. Said for his contribution to science, research, and innovation. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi ta'ala wabarakatuh.
Thank you, Professor Dr. Muhammad Zulfaizal. Ladies and gentlemen, Alhamdulillah, we have now arrived at the highlight of today's program. It is my great honor to invite Professor Dr. Syed Inayatullah Shah to deliver his highly anticipated lecture entitled Medical Physics and Imaging, the Synergy of Science and Technology in Modern Healthcare. Let us give him a warm welcome.
Bismillahir Rahmanir Rahim. Assalamu alaikum. Alhamdulillahi Rabbil Alameen. Wassalatu wassalamu ala. Bismillahir Rahmanir Rahim. Assalamu alaikum. Alhamdulillahi Rabbil Alameen. Wassalatu wassalamu ala ashrafil anbiya wal mursaleen wa alihi wa sahbihi ajma'een. Rabbish rahli sadri wa yasli amri wa ahlul uqdatan min lisani yafqahu qawli. I am thankful to the audience. I would like to first thank you to Professor Dr. Samsul bin Darman, member of the IUM Board of Governors, Associate Professor Dr. Muhammad Arifin bin Qadri, Deputy Campus Director, Professor Dr. Ahmad Aidul Arafat bin Zulkarnain, Dean Kull of Allied Health Sciences, Assistant Professor Dr. Iqbal bin Jamaluddin, Head Department of Diagnostic Imaging and Radiotherapy, and Deans, Directors, Deputy Deans, Heads of Departments, Professors, Associate Professors, Sisters, Madams, Brothers, Assalamu alaikum. Today I am going to deliver the lecture, which is an interdisciplinary lecture, and I'm going to highlight the synergy of medical physics and medical imaging in the medical healthcare sciences. So before I go to the main lecture, this is the structure of my lecture: Wonders of Physics, Medical Physics, Diagnostic Imaging, Radiotherapy, Radiation Protection, Research Interest, and Overlooked Venue. I'm going to recite few verses from Quran in order to refresh our belief in oneness of Allah. Bismillahir Rahmanir Rahim. Alif Lam Mim. ذلك الكتاب لا ريب فيه هدى للمتقين ولو إنما في الأرض من شجرة أقلام والبحر يمده من بعده سبعة أبحر ما نفذت كلمات الله إن الله عزيز حكيم قالوا سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم. It is just a reminder to us that the noble Quran that was revealed to our Prophet Muhammad sallallahu alaihi wasallam is the true book, and there is no doubt in it, and it's a guide for those who are mindful to Allah. And Allah is all-knowing, exalted, might and wise. And we do know nothing. We have no knowledge. Only what Allah has taught us. Synergy of science and technology. Synergy is actually the integration of science and technology, and it is true reflection of the line from the I song. Together we make the world a better place. And in my mother tongue Sindhi language, it can be expressed as Batabara, means two are not 1 plus 1 is not equal to 2, but they are more than 12. So when two people work together, then the outcome is better, more than the two people. So here I'm going to explain later on the synergy of science and technology in terms of the the medical imaging, healthcare sciences. So science explores the why and how of events, whereas the technology develops solutions based on scientific understanding. For example, AI enhances the accuracy in the diagnosis accuracy significantly when AI works with the medical imaging. And there's a message in this slide as well that we have to work together. So when we work together, then the yield is the deeper research insights. Well, I'm going to talk about the wonders of physics. Actually, in Quran, we are invited, our attention is invited to observe how the sky has been raised without any support, and how it has been beautified. So we have to observe, but how to observe it, how to study it, how to know that. So physics is a subject, a science that tells us that how this universe works, It has not only the applications in the other sciences, but it has applications in many areas, in engineering, in technologies, in natural sciences, where physics has the roots in for example, mechanical engineering, electrical engineering, semiconductor technology, laser technology, and of course, medical imaging technology. So it's not just subject, but it explains the magic of our universe. For example, gravity holding us down. If there are no gravity here, then we might not be here. It be like we are in space. So this gravity is explained by the physics. Now, if you go to the next topic, which is physics in modern medicine, so under this we have imaging technologies like we have X-rays, ultrasound, SPECT, and they all are based on the physics principles. And radiotherapy, where radiotherapy we use the ionizing radiations, for the treatment purposes. So we treat mostly the cancer with those ionizing radiations. And biomechanical devices, for example, pacemakers and surgical lasers, they apply the physics principles. Nanomedicine deliver drugs using Brownian motion, which is again the physics principle. Physics has application in artificial intelligence as well. This is somehow a background, I mean, under the wonders of physics, where physics has applications. So, for example, we have integrated circuits now in semiconductor technology, where we develop the CPUs, GPUs, and their functionality. And for memory storage, we use a magnetism of quantum tunneling in storage. And then neural networks, we use statistical mechanics in AI algorithms. Monte Carlo methods, we use a particle physics simulation for AI training purposes. Well, there are two books published by a professor, American professor, Physics and Future Presidents, and another one is the Physics and Technology for Future Presidents. An introduction to essential physics every world leader needs to know. So it is a very important subject, and in this book, the author has actually explained the simple physics principles for actually educated lay persons for them to understand the physics. And in another book, in Physics and Technology for Future Presidents, this is for students and other persons as well, not those who are majoring in physics, but other persons where they can learn about the application and importance of physics in for example, medicine, health sciences, in nuclear energy, renewable energy, and this book has been taught in 20 universities, 20 American universities. Now I move to the medical physics. So medical physics applies physics principles to medicine, like electromagnetism, X-rays, alpha rays, gamma rays, beta rays, and it is very important in terms of its outcome, because when we use this in medical sciences, then we treat the patients. So we save the lives of the patients, and we reduce the risks as well, and we drive the innovations in medical physics. Historically, it began with the discovery of X-rays in 1895 by William Röntgen, and then followed by the radiotherapy and nuclear medicine. Well, there's a timeline for diagnostic imaging. It was X-rays were discovered in 1895, then ultrasound 1956, gamma camera in 1957, PET in 1977, PET scanner in 1961, then commercial ultrasound 1963, and then we have now the hybrid imaging systems. They were available, commercially available by 2010 and so on, and we have now photon counting CT scanners. They are most advanced now. So with those we can have a very nice high quality images, so that the disease can be diagnosed easily and accurately as well. In more detail, the scope of medical physics is in these areas, like as I mentioned, in diagnostic imaging, where we have CT, we have MRI, we have PET CT, then we have radiotherapy, where we use the external beam therapy, brachytherapy, and then radiation protection, we have patient safety, we have worker safety, we have public safety. For equipment quality assurance as well, we do the calibration, we do the maintenance, we do the testing as well of the equipment. Here I have shown some medical imaging modalities like X-rays, CT, MRI, SPECT, PET, hybrid imaging, ultrasound. These are all the medical imaging modalities. And with the help of these imaging modalities, we can detect the disease early, and we can monitor the diseases in a real time. Well, there's a radiotherapy. In radiotherapy, normally we focus on the cancer cells, so they are targeted. Precisely they are targeted, while the minimum harm is received by the healthy and normal tissues. There are some advanced equipments, state of art, like the LINAC, IMRT, VMAT, and CyberKnife. They can be seen down there. And we do have the treatment planning simulators. Before we treat any patients, we have to do the treatment planning, where we have to measure the doses that need to be given to the tumors or cancer cells to destroy them. Or at the same time, there's a quality assurance as well. So physics is applied in quality assurance as well, in order to check the performance of these systems, whether they work properly or not, before the use to the human beings. Well, in this figure, the different modalities, imaging modalities, and as well as radiotherapy modalities are shown, where there is a strong root of physics in all these imaging modalities, from machines to the treatment of the patients. Well, we do the radiation protection because we know that these radiations, they are harmful to the living cells. So we have a guideline which is explained by the Alara principle. We minimize the exposure by applying the Alara principle as low as reasonably achievable. We do use a shielding from the radiation, so that the radiation is absorbed by the shieldings. Well, shieldings, they are designed based upon physics principles, like the interaction of radiation with the matter, absorption, and the attenuation coefficient. And we do monitor the doses using the OSLDs, which are the dosimeters, TLDs. But they work on the basic principles of the physics, interaction physics with radiation, their dosimetry, their measurement. And we do follow the regulations developed by the IAEA, AELB, which is Malaysian Atomic Energy License Board. We follow these regulations in order to minimize the patients and do the radiation protection. And we do also the quality assurance of radiography equipment like fluoroscopy, mammography, dental CT, in order to the compliance of the quality assurance rules and regulations. And also the main aim is to measure the dose and dose rate so that the patient can receive the minimum dose and maximally they can be benefited. Well, here is a history of the equipment, evolution of the equipment, like then and now. We have, in earlier days, we had the equipment where we can see there's no protection of radiation, but on the right side, we can see now we have digital systems. Digital systems, they are their outcome is very excellent, brilliant in terms of image quality and as well as in terms of radiation doses. So radiation doses are now less, which is the most important the issue in radiography, and we can save the time, and there's no need of using the dark rooms or the film processing that it was done earlier 10 years ago. Here we can see the difference between the CT systems few decades ago and now. So there's a lot of development in the equipment technology as well. So we can now, these systems, they are faster as compared to others. Their image quality is better. So the diagnosis of disease can be accurately assessed or measured. So the patients, they are properly managed. We have a principle regarding the, we justify, when we apply the radiation dose, then we justify that we have to give more advantage than the disadvantage, because we know that the ionized radiation, they are harmful to the cells, to the living cells. Well, in this slide, we can see the MRI systems. Nowadays, we have very latest MRI systems as compared to the few decades ago. This slide shows the nuclear medicine equipment. In earlier days, we had the gamma camera on the left, and now on the right side, we have a latest one. Also, these cameras, they work on the basic principles of the physics, from the radiation detection, measurement, and the image reconstruction, then image display. So there's the involvement of physics in it. Well, this one is the radionuclear imaging PET system, positive emission tomography system. Then and now, the purpose to show these slides is that how the technology has evolved. the things that are changing, how rapidly the things are changing. So we are getting more nicer, more efficient systems or equipment so that we can accurately measure the doses. We can accurately diagnose the diseases, sorry. Well, we have now latest technology, which is known as hybrid technology, where two different modalities, they are merged together, like PET-CT. PET is the functional imaging, and CT is the anatomical imaging, and SPECT is again the functional imaging technique, and CT is the anatomical. So we need both. When we need to accurately diagnose diseases, then we need the anatomical and functional informations. So when they combine together, this we can say is a synergy of two different technologies. So when 1 + 1 they are together, then their outcome is more than 1 + 1. In simple mathematics, 1 + 1 is 2, but it is not true here. So 1 + 1 is more than 2. So the outcome is much, much better than these two. Similarly, we have PET MRI system. So PET, they are more efficient as well as compared to the stand-alone imaging techniques. Now, since the technology is advanced, so there are advancements in the medical imaging technology as well. It has transformed the whole medical physics. Like we have AI in image analysis, so it's used for image analysis and dose prediction in the field. Then we have adaptive radiotherapy, where it utilizes the real-time imaging for precise treatment, imaging at the same time. There's imaging as well as there's treatment of patients. And then we have 3D printing. 3D printing creates phantoms, which guides for radiation therapy procedures. And we have theranostics. In theranostics, we combine diagnosis and therapy into single approach. At the same time, we use the same radioactive material that is used for the imaging purposes as well as for the treatment purposes. Now we have robotic radiotherapy as well. Robotic radiation therapy, which enhances the accuracy in treatment and delivery. Nowadays, in one case that has very much circulated in the media, that one doctor has treated a patient. He was doctor in Dubai, but the patient was in China through the robotic technology. So technology has advanced. That's why the medical physics field has advanced as well. Of course, this field has advanced, but there are some challenges as well, like shortage of professionals. According to the report of IAEA, which is 2023 report, so globally there will be shortage of medical physicists about 30% globally. And the other challenge is the high equipment, of course. For example, we have one digital radiography system is cost 1.5 million, and then one ultrasound system that costs 1 million. And the third is the technical accessibility disparities, unequal access to medical technologies. So these are the limitations. They need to be addressed, and as well as need for ongoing training, because the technology is changing. Maybe I can say, I won't be wrong to say day by day that the technology is changing. So there's the need of the training as well. So the persons related to this field, they need to be trained so that they can overcome the issues. I mean, they can be updated. They can update their knowledge, so they are not left behind. Well, future horizons, they are going to personalized medicine. In personalized medicine, where tailoring treatments based on individual genetic profiles, genetic profiles. So it's personalized treatment, and we have AI, and we have come across big data as well. So we utilize the AI in big data in order to analyze the data, and we can plan the healthcare for future healthcare. Well, this one is the the shaping the next decade regarding the medical image technology. This poster has been designed by a medical physicist. Actually, every year on 7th November, International Day of Medical Physics is celebrated. So in this poster, this is a winning poster. In this poster, it has been shown AI-assisted imaging. This is the future of 10 years, future of the medical imaging technology. We have proton therapy, we have therapeutics, we have PET MRI, we have robotics, and we have digital twin models of SPECT and CT. In digital twin models, we can see someone is far away, is scanned, but virtually we can see his image another place at a distance. So this is the next decade's hot areas in medical imaging, and we do have the cyber knife as well, telemedicine as well, since the telecommunication has advanced, so we can perform the surgeries and some tests remotely using the telecommunication technology. This is the conclusion of this portion. So where medicine and machines unite to serve humanity. In medical physics, where medicine and machines, they unite. It is again a synergy, unite to serve the humanity. But behind it lies a synergy of multiple disciplines and dedicated human efforts. So there are multiple disciplines. There's engineering, there's a physics, there's a chemistry, there's a IT, there's a computer. So they all are involved, and of course there's a contribution of the range of disciplines and the experts like the medical physicists, radiographers, oncologists, radiologists, doctors, and they all are shaping the new horizons of healthcare, modern healthcare. Now I'm going to share my research interests, and they have been divided into three. I have research interest in three different areas. One is in the radiological imaging for scatter correction. Another one is to development of quality control phantoms for radiological imaging systems. Then we have the other one is radiation dosimetry and radiography. These are the important areas among the others in medical physics. Well, here I have shown some publications, some of the publications there, but I'm not going to talk them. Now I'm going to talk about the scatter correction techniques in single photon emission computed tomography. This is my work actually that has been published already. So here actually there's a big issue in nuclear medicine imaging about the scatter radiation. The presence of radiation gamma photons in SPECT data degrade the quality of reconstructed images. So when the quality of reconstructed images is degraded, then it is difficult to diagnose the disease accurately. So we need to remove the scatter radiation from the image data. There are different techniques actually that I'm going to explain in the coming slide. But what is the effect of scatter radiation on the images? Generally, the image quality is degraded because we have to, specialist doctors, they have to view the image, analyze the image, then diagnose the disease. And this issue is because of one of the reasons is the sodium iodide thallium detector. Sodium iodide thallium detector is the radiation detector, and it is used in the gamma cameras. Gamma camera is the equipment that detects the gamma rays, scan the patients, then we produce images from the data. Because of its poor energy resolution, still there 30 to 40% fraction of scatter radiation is present in these in the image data. If we look at this image, then we normally say the energy window or the spectrum here. So we can see this is the scatter peak over here. Our scatter radiation is there. We have to get rid of from those scatter radiation. As we know that in nuclear medicine imaging, we inject some amount of radioactive material into the patient's body, and patient becomes a source of radioactive material, and gamma ray they emit from the patient body. When we inject radioactive material into the patient body, then those gamma rays interact with the cells or tissues in the patient body. Some they are absorbed there, like we have number 3, it is absorbed there, and it does not come out from patient body, so we lose the information. Number 1 is the true one. It can be reached to the gamma camera as recorded, but it is not deviated. The 2 is a problem. The number 2 is problem. Actually, its origin is somewhere in other place, but it travels, it scatters, travels, and reaches the gamma camera, and it gives the false position information. And our aim in nuclear medicine imaging is to determine its actual position from where the gamma ray has emitted. Then it will show us the actual location of the emitting gamma ray. So we need to remove them. So there are different scatter correction techniques, like we have computational techniques, we have energy window techniques, we have the system based like single, dual, and multi energy windows. However, they do have the problems. They do not function properly, and some methods they are very expensive. So the one that I have done here is the material physical filter technique, which is very simple technique, cost effective, and easily mounted on the gamma camera head in order to improve the image quality and remove the scatter radiation before they reach to the gamma camera detector. Well, in this slide, I've tried to show how to select that filter, a material filter, like tin. So in this graph, we can see the curves of different materials, copper, tin, lead, and tungsten, and the absorption fraction of different gamma ray photon energies have been calculated. So if we look at this curve and these other 3 curves, yes, there's a more attenuation, but the problem is that, of course, there will be more scatter. Scatters will be absorbed by the filter, but at the same time, it will absorb the true events that we do not want. So that's why the decision was made to select this one. So this one is in between. And copper one does not absorb many, whether they are scatter photons or the unscattered photons. So the decision reached to select the tin material of 0.2 millimeter thickness. Well, this side is the physical filter, and these are filters. They are displayed over there as well. Now, how does a material filter work? So in this graph, we can see that this is the organ, and from organ gamma ray is emitting, and which is unscattered, and it can cross the collimator. Collimator is the one component of the gamma camera that we can see is over there. So it can easily cross over there, and then another one scatter radiation that can pass through as well, that can reach to the detector as well. Okay, but in this case there is no filter. But in this case we have put the filter over here. So now what will happen? That scatter radiation will be absorbed. Now scatter radiation is a physics principle that when radiation interacts or scatters, then it loses some amount of energy. So it has less energy as compared to the unscattered radiation. So it will be absorbed by the filter, and it won't reach to the gamma camera. And it's also good to remove these noise. We call them as noisy signals as well before they reach to the image data. the advantage is that when we remove them before the processing, then we will develop less noisy signals, because their image reconstruction techniques, they do produce the noise while we produce the images. So it's ideal to remove those noisy signals before they reach the gamma camera. So this is the advantage of this filter technique. We can call it as an online scatter correction technique as well. Well, we do not do the studies on human beings. I mean, these research studies, so we do have phantoms. So this is very, simple phantom, and this is known as the R.A. Carlson's phantom. And in it, we have different inserts. And these inserts mimic the lesions. For example, in this case, we have heart lesions, we have core lesions. Actually, we come across two types of lesions in nuclear imaging. Heart lesions, they are like tumors, and core lesions where there is no distribution of radioactivity. For example, in coronary artery disease, when the artery is blocked, then blood supply is less over there to the cardiac muscles. So there is no distribution. Normally, we inject the radioactive materials into the patient's body via IV, intravenous. So it can distribute into the body through the blood stream. So when there is no blood supply, means there is no radioactivity. Okay, so we have here cold areas, we have hot areas. But this work is mainly on the cold areas. These cold areas, they have different sizes. Well, they mimic the lesions, abnormalities in the human body. Of course, this is a very simple. This is very simple phantom. In reality, the lesions, they are not of a regular shape. They are irregular, any shape. They might have any shape. But in order to have something easy procedure, to at least to measure something, so these types of simple types of phantoms have been designed. Well, the data were acquired, in a similar way as we do collect the data in patients, okay, and then the spectrum was plotted. Well, again the count rate and the energy. So we can see this region, this area. Well, the red one is without filter, and the blue one is a with filter one. Okay, so we can see there's a reduction in this area. According to the studies, out of 30 to 40% scalar radiation, 80% is present in the lower part of the photo peak. So this shows that the filter is removing the scatter radiation. So the data was reconstructed accordingly, according to the standard procedures that we apply in clinical practice as well. And the result is, if you look at this one, this is the image of that core regions, and no filter was applied over here. So these are small core regions over there, the blue one. And you look at here, then with the filter one, we can see more clearer and more number of lesions. So it means that the image quality has been improved by the filter, and filter removes some of the scalar radiation. Not all. We do not claim that all has been all scalar has been removed. It's impossible actually, but scalar radiation has been removed. So that's why we have improved the quality of image is improved. Okay, so we can diagnose a disease easily, especially we have issue when we have we want to detect a small lesions as compared to larger in size. So small lesions, detection of small lesions is very difficult as compared to larger one. So we can see here the images of the lesions, they are clearer here. Okay, and the second parameter is the contrast. So if you look at this graph, then we can see this one is with filter, and this red or purple one, the red one is without filter. So we can see the contrast has been improved as well, which is clear from this image. But there is not much difference in the larger one, But there's a big difference, a significant difference between the contrast of with and without filter. And the conclusion reached that the filter, material filter, sometimes we say physical filter or material filter, that remove these gamma photons prior to their registration projection data, and is known as the online scatter reduction technique. And it reduces the noise in the image, and it enhances the small lesion detectability or co-region detectability. It enhances the contrast, and that indicates the utility of material filter technique in technetium nitrogen. So in continuation of that, we applied another type of filter. We did the other studies. Here we use the zinc 0.2 millimeter thick filter, and we did the further investigation in order to check the impurity of the material, because we purchased it from the hardware shop. Because it's low cost, we purchased from the, so we wanted to check its purity. So we went for the energy dispersion X-ray spectrum. So we have found that zinc is 87%, and the other one is copper and oxygen. So we can say that yes, it is pure. It's not 100% pure, but 87% is quite high number. And on the other side, we have a check is uniformity, whether it's uniform or not. So we have been through, the material been through the surface morphography. So we can see that the image is very, very smooth and flat. Actually, a filter should be a flat in order to achieve the optimum results. Filter means here with a physical filter. We do have the digital filters as well. They remove the noise. And this is the construction of a physical filter, where we can see the schematic diagram of the zinc, 0.2 millimeter, this one, and over there, this one is the filter. And the size of the filter is according to the size of the head of the gamma camera. It depends the size. And the aluminum strip, which is a frame that's made in order to hold the filter state in a state position. And then we can easily put the material filter on the gamma camera head over the collimator. Well, this is the data collection. Again, we are using the same phantom. But in this case, we are going to see the co-regions. We did apply some other filters as well, like we applied copper, we tested the aluminum as well, and different thickness over here. So let us see the results. Well, this is the cross-sectional view of the hot region. Now, this in earlier case was cold region, but in this case is a hot region. So we can see the no filter image and with filter image as well. So here actually they are disconnected, and really they are disconnected. There are no connection, but in the image where there's a no filter has been applied. So in this image we can see they are connected here, but over here in this case we can see there's some distance. They are disconnected. So this indicates that the scalar radiation has been removed by the filter, and there's an improvement in the image quality, so we can easily diagnose disease. And these images were further analyzed by using the images software. Well, the result of a conclusion of this study was that the hot region, earlier case cold region, and in this case hot region detectability, particularly small lesions, was enhanced. In terms of size of all hot regions, with the material filter provided a closer size to the original one. So the results of the material or physical filter suggest the use of zinc 0.2 millimeter clinical. Now we are moving forward to the clinical one. Clinical technetium. Earlier just a phantom study. This is a phantom study as well. But on the base of these results, we try to apply this technique in clinical situations. But the condition is that before we go for the clinical, we have to scan the phantoms with some organs. We do have different types of phantoms. We are simple. This is the simple phantom. We are going to see in the next few slides a phantom that is closer to the human body. That mimics the human body. So we are going to scan that one. We want to see the results of the other study. Now in this case, we did do the study is something like the cardiac tomography study. And again we use the zinc filter, 0.2 millimeter thick. And this is the phantom. This looks like the human body. Of course, it's not 100%, it is equal to the human body, but looks like the human body is more closer, so that we can have better results when we scan this type of phantom. Well, this is the heart, and here defects are shown over here. Heart defects in myocardium. Where in myocardium, these defects appear because there is no blood supply. The arteries are blocked, so there is no blood supply to the cardiac muscles. And the system here we use is installed in Kull of Medicine, Jalan Hospital. We did the study there with Dr. Shahri there. So we found, in simple, we can see this image and that image. So again, this image is the without filter one, and this is with filter one. And the important point to share with you is that all the parameters, data acquisition parameters, they were used similar to the patient studies. So we can compare the data of the results of this study with the patient studies as well. Over here we can see that there's a big gap, but over here this connected one. So this connection shows that still there some radiation is there, scatter radiation is there. Well, scatter is actually that carries fast position information. Its origin of emission is different, but it travels in such a way so that it still is detected. Okay, so we did another study, which is the polar map study, and here the segment number, there are 17 segments. So segment number 7 and 12, that shows the gamma scatter radiation. They have been removed from the anterior defect and lateral defect, the anterior and lateral defect. And the result and the conclusion is that this technique may be used in clinical studies in general and myocardial SPECT imaging in particular. So this one is the study done by using the phantom with the organs, like the human body, human organs. But the results of this study hasn't been applied on clinical studies because there are a lot of limitations and conditions in order to the study the humans. So it hasn't been tested yet. But from the findings of the previous study and this study, it shows that it has a potential for the application in clinical studies, especially myocardial studies. But this filter has been designed only for the technetium-99 radioactive material, because technetium-99 radioactive material is most commonly used radioactive material in single photon emission imaging. Almost above 90% studies they are done with the technetium-99 radioactive material with a suitable chemical compound. Now we move to the next one. Next one is another area of interest, is the phantoms. So phantoms, they are mostly used for the quality control of the equipment, and quality control is important as well. We have to check the accuracy or performance of the systems before the use for patient studies. again, I would say that it is impossible to check the systems or test the systems on human studies. So these phantoms, they are used normally to study the system spatial resolution, uniformity, linearity, sensitivity, image contrast, and signal price ratio in the image. And also they are used in order to test the algorithms. There are a lot of algorithms like image reconstruction, image enhancement, scatter attenuation correction techniques. And the most important advantage of these phantoms is that we knew the information of the image of the object beforehand. Because these are the phantoms we can view. We can compare easily the image quality with the object that we scan already, because the object we knew is shape, is size. So this is the advantage of using the phantom. So I have developed one phantom, actually a whole phantom, but I want to explain here only a tank. Actually, these phantoms, they are comprised of two parts. One is the source tank, like this one, and then another one, they are inserts inside there, like as I explained earlier, cold region, hot region, linearity. Okay, so this phantom is Jazzix phantom, and in this phantom, these screws, in order to tighten the cap of the cylinder, the thumb screws, they are used, made from the plastic material. So when it is used heavily, then they are damaged. Okay, so this is the issue. Then the phantoms, especially tank, cannot be used more. So what I suggest is that to develop a new tank with a screw cap, this type of cap on it, so we can screw and unscrew it. And there's another issue with these phantoms. When you have to prepare a phantom, then we have to make sure that there's no air in it, no air bubble in it. If there's air bubble in it, then the artifacts in the image, they are produced, they are developed. So we have to make sure that there are no air bubble in the phantom. So I have designed the small cap. These actually small holes are there, their cap as well. They are inlet of water, inlet of radioactive material. So I'm going to show you in the next slide. This is the design actually of the phantom tank. This is a screw, and this is displayed here as well. So it can be screwed and unscrewed. And these are two other smaller caps, inlets in the phantom tank cap, phantom tank cap. Okay. This is this has been patented. This tank is patented in June 2020. Yeah. Okay, this is the other design. Actually, this is the insert inside it, but I'm not going to discuss this insert here. Well, this one, how to remove the air bubble from the tank. So this small inlet has a rubber cork in it. So what we do, we fill it with the water first, and then we try to remove the complete. We have to fill this tank completely, no air bubble at all. But it's very difficult to remove the air bubbles. So in this type of the design, the rubber cork, so we can have the only needle of the syringe. We push it until that air bubble, we reach the bubble, and we have to tilt the phantom in such a way so that the air bubble comes under that area. Okay, then we have another syringe with some water or maybe radioactive material. So we inject the radioactive material water into it. The air will come out from this needle, the empty needle. So this is a technique how to remove the air bubbles easily from the phantom. And over there we can see the scanning of this phantom. So we have tested this phantom as well. we do have this type of phantom, this type of inserts actually. This one I have modified as well from the R.A. Carlson's phantom. You can see here the heart regions. This is the solid block of acrylic material where holes are drilled in it, and they mimic the what you call the heart lesions. And over here we have core lesions. Core regions, so they are rods actually, solid rods. So and around solid rods there's the radioactive material, and in these holes there's radioactive material. So they mimic the heart areas. And the beauty of this region, this heart and core region, is that it gives us the same image, because core regions are affected differently as compared to the heart regions in nuclear medicine imaging. So we want to compare the impact on the heart region and core region. So these are the images of the uniform region. This is the image of the heart region, the V shape and the two holes over there. And this is the image of the cold region inside. Okay, so these cold regions, they are actually abnormalities in the human body, cold and hot area. Heart is normally considered as a tumor. So this one was actually there another phantom we did develop. Actually, it's my PhD student. She did PhD during the COVID time, so she was not here. And then I went to Pakistan. Then I took her thesis, so I'm handing over the thesis over it. Well, I've just put this photo, this drawing here, because it's not patented yet. It's not even the patent even hasn't been filed yet. So it's not worth to show a display here, a disclose here. So there's a second phantom as well, and it can be, processed. A patent process can be processed in future maybe. Then the third part is the dosimetry. Third is the dosimetry. So in dosimetry is in radiography, dosimetry radiography. So it's a big issue in radiography about the radiation dose. We do scan the patients, but of course they do receive the higher doses as well. And with the systems is that they do exhibit non-uniform radiation intensity. So the organs, they receive the non-uniform radiation dose. They receive the non-uniform radiation dose, but in practice we take the doses, average dose to the organs, but which is not true. The organs, different regions of the organ, they receive different doses. So we have tried to map the radiation dose to each organ using the OSLD, optically stimulated luminescent dosimeters. And we have done this study again on the phantom. This is a phantom in our department. This system is installed in our department. So we collect the data, and this one, the latest study, it has been published recently in 2025. Well, this is the way how we map the radiation dose. Like, well, in the abdominal region, we have liver, we have kidneys, and we have spleen. So we selected three organs, and we divided each organ into different segments. So we have 8, we have 3, and we have 1. And then we place the nanodot OSLDs corresponding to each location of the organ, and then we expose. We expose by selecting different exposure factors like different KVP and MAS, and then we can see the difference here. We can only look at the blues. There's a lot of variation, and this shows the different segments of the liver. And this study has been done on anode-oriented X-ray beam, because there's a difference in the exposure radiation orientation with respect to the orientation of the X-ray system, anode and cathode orientation. So I move to the next one. The same situation is in the kidneys as well. And another thing is that when we increase the exposure factors, then the organ, they do receive the higher dose as well. Okay, so this is cathode oriented X-ray beam. So when they're cathode oriented, then The organs, they receive higher doses. Well, conclusion of this dosimetry is patient position is important. So we have to place radiosensitive organs away from the cathode side, which can reduce the unnecessary exposure. Then beam orientation, choosing the right beam orientation can affect organ dose distribution. Exposure settings like KVP and MAS, then collimation as well. So future research can be done on checking additional parameters like exposure factors, phantom orientation, and patient-specific models to further enhance dose optimization. Now this is the third part. It is more like on the Tawhidic one. So the Quran is the book of guidance. It is not a book of science. It's a book of guidance. As revealed to our Prophet. And the first verse of Quran is Iqra bismi rabbikal ladhi khalaq, khalaqal insana min alaq. And the main thing is the recite. Iqra means recite. And it's a creation. So recite doesn't mean only recite. Recite means we need to explore further. We need to understand. It's not just reciting or reading a thing. We need to understand. We need to explore. So I'm linking this with the nature-inspired, the research. Okay. And we have a lot of verses in Quran that they invite us to think, to explore, seek the knowledge, use the brain, intellect. Like this verse, He has subjected to you all that is in the heavens and the earth, all being from Him. Verily, there are signs in this for those who reflect. So there are signs in the Quran as well, for us to think. And another word is, in another verse, observe. Did they never observe the sky above them? How we build it and beautify it, and it has no cracks. We have to think on it. We have to observe it. Then another one verse, do these unbelievers not observe the camels, how they were created, and the mountains, how they were fixed, and the earth, how it was spread out. So there are a lot of commands from Allah for us to think and to get benefit and be benefited. And there's a preachings of Prophet Muhammad sallallahu alaihi wasallam regarding the learning the knowledge as well. So we have to learn as well the knowledge. Well, I'm not going to talk much on the Tawhidic epistemology, but it is the integration of reveal and acquire knowledge, naqli and akli. Viewing nature as signs of Allah leading to ethical and purposeful innovations, which encourages humility, accountability, and sustainability in scientific exploration. So we have the title is Allah's wondrous creatures and innovations. So we have shrimp eye, and we have fruit fly eye. We do not like the fruit fly, but eye is very, very unique. Compound eye is very unique. So what has been done others? We have done nothing, but what others have done, like this person, and this is strategy 2025. So they have developed insect-inspired imaging system. Okay, insect-inspired, like butterfly. So what is the advantage of this one? Fast and low light imaging. Low light, in dim light. Some fly, they fly in the night, in the dark, but they find their path. They find their food as well. So their visual system is much better than the other creatures. Another study is using the shrimp vision, where they have used this study has been done in 2024 as well, and the device is can detect the tumor as well, because the shrimp vision is very different, and it detects the polarized light as well. This is again physics again, polarized light. And then another one is a group of researchers in 2021, They have again developed the 6-channel image sensor, and that's used for the tumor location. Provides information about tumor location unavailable from a single instrument. And another one is ultra-thin digital camera. This study has been done in 2018. And the insect is Xenos pacae, which exhibits distinct benefits for high resolution, high sensitivity camera. So these are the camera, this ultra-thin digital camera. They have developed based upon the vision principles of these insects. Well, in Quran, it says again to observe, to think, to use your intellect. So nature offers models. Okay. Well, when we do the research, then we go through a lot of literature, we go through the article, journals, discussion, take a lot of time, and then after that we develop some model for the research. But nature provides us models, already tested models, like the flies, these things, they're already tested, and we haven't got any benefit from the models, tested models provided by Allah. So I have taken this line from Let's Lead the Way, from our IIUM song. So can we develop a multi-purpose super eye, a camera, a sensor? Can be used in defense, can be used in medical imaging, can be used in surveillance, can be used in many areas, in AI maybe. Can we develop? Yes, we can develop, but we need a group. We need to follow the synergy, the term synergy. Synergy means we need to work together. Means we need to work together as physicists, a medical doctor, engineer, a computer science, a group of people, we can sit together, then we can develop. There's another one, this is my research actually, I did on it, on the bats and dolphins. They do emit the ultrasonic signals, and we do use the same principle in ultrasound imaging. And these are very fast in terms of the response and very accurate. They can detect their objects in no time, exact distance, exact shape, their movement as well. So by conducting the research on these animals, I mean the birds, the dolphins or bats, we can generate, this is actually a perspective article. It's not a practical or a data collected with perspectives. So with that we can develop transducers, data acquisition and image communication software. So we can develop a new ultrasound system following the ultrasonic emission principles of bats and dolphins. Because these are models here. Models are tested. And these are gifts from Allah. So we have to get those gifts, and we have to be benefited from those gifts. So we did the study in continuation of the previous one. We did this study in our department using the Phantom and ultrasonic sound system over here. That's available. Since this was a very rough method, we used a probe. Actually, these bears and dolphins, they emit ultrasonic signals simultaneously, multiple signals simultaneously. But our PROF, they do not emit the ultrasonic signals having different frequencies simultaneously, but they emit. So we can develop a transducer that can emit the ultrasonic signals simultaneously, like these bears and dolphins. Then we can develop the instrument so that it can process all the signals simultaneously, like the compound eye of these flies. They have a lot of eyes, but they process, each eye process simultaneously at the same time. In the end, they have the image in their brain. So we can do something like that as well. Well, here this is leading the way. We do have the glass frogs. Sorry. We have glass frog. Glass frog. This is a transparent frog. And this collects the red blood cells into liver, become transparent. Can we do something on this one to develop? And we can see the inner organs without X-ray or MRI or something like that. We can do, because Allah says in Quran. These are models. These are models, tested models by Allah. And Quran is, there is no doubt in Quran. No doubt. And another fly, I don't know whether it's taking any, handling the emergency or not, I don't know. But it's taking something. Can we develop something from this fly? Can we? Yes, I think we can. So I think probably these are the last few slides. Medical physics and imaging, Tawhidic wisdom, from the atom to cosmos, from the student to lecturer, from the patient to the practitioner, all of creation speaks his Allah's oneness. So by doing this research, we can go closer, we can come close to the Allah. And we can witness the oneness of Allah as well. So this lecture was shared act of learning for sake of Allah at IUM, where knowledge is amana. Let us remain connected in our mission to educate, to heal, and to worship Allah subhanahu wa ta'ala through science and technology. Through science and we can worship. The research is a worshipping of Allah as well. Because we know, for example, cell, human cell. We do the research, we are amazed to see the function of the cell that is created by Allah, not any human body, another person. In the next slides, I owe them my success, my father, my uncle. I have to say a lot, but I have no time. This is my father, my uncle, and the uncle. This is my uncle as well as my father-in-law as well. And he left us in his very young age, only 39 years old. He was professor of chemistry, organic chemistry. And my other family members in Pakistan, my mother, my sisters, other brothers, and other family members. Of course, my family members, they are sitting here. And first and foremost, Allah, His blessings. And thanks to my mentors, collaborators at University of Sindh and ICT trustee, University of Surrey, King's College London, University of Science Malaysia, Prof. Ahmad Zakaria and other team, and my former students, current students as well, and my colleagues at International Islam University, Prof. Dr. Aidil, Prof. Zul, Associate Prof. Dr. Arifin, Dr. Iqbal, Dr. Zafri, some other colleagues, Dr. Muzaffar, Prof. Muzaffar, some other from this side as well. And this one is the thank you card from my final year student they give me because I am retiring today. After a few hours, I won't be no more active staff of the UIA after 5 o'clock this afternoon. This is the thank you, terima kasih banyak, thank you for your attention. And this photo was taken by Dr. Zaf yesterday. Just he said you have to put there, so I put there. And this is a quote from me, because I never say goodbye. In academia, there are no true goodbyes, only the enduring echo of shared ideas. May those echoes resonate across time, and may our paths converge again in the pursuit of greater knowledge. So no goodbye, see you inshallah again, jumpa lagi. Terima kasih. Thank you very much.
Thank you very much, Professor Dr. Said, for such an inspiring lecture. We are deeply grateful for your unwavering dedication and for serving us so selflessly for the past 16 years. Can we give a standing ovation to Professor Dr. Said, please?
Thank you.
Thank you very much, Professor Dr. Syed. You may return to your seat. Ladies and gentlemen, as we continue to honor Professor Dr. Syed's remarkable journey and contributions, we now invite you to turn your attention to the screen for a special video montage prepared in his honor. Please enjoy.
Professor Syed Inayatullah Shah, A Journey of Dedication, Discovery, and Impact. Professor Syed Inayatullah Shah was born on February 9, 1962 in the village of Amin Lako, district Madiari, formerly Hyderabad, Sindh, Pakistan. He is the fourth among 7 siblings in a close-knit and nurturing family, where the values of hard work and education were instilled from an early age. His educational journey began at the Government Boys Primary School in his native village, followed by studies at the branch of Government Boys Middle School Pir Jando in Amin Lako, and then at Government Nationalized High School Mensora, Depar, near New Sadabad, where he earned his middle standard certificate. He continued his secondary education at Makdum Ghulam Haider Government High School, Boys, Hala New, obtaining his secondary school certificate. He pursued his higher secondary education in the pre-engineering stream at Government College Hyderabad, now a university, and later at Sarwari Islamia Government Degree College, Hala New. In 1984, he graduated with a Bachelor of Science in Physics from the University of Sindh, Jamshoro, with first-class honors, securing 3rd position. The following year, he earned a Master of Science in Physics from the same university with first-class honors and 1st position, laying a strong foundation for a future in academia and scientific research. With a strong aspiration to advance in the field of medical physics, he received the Central Overseas Training (COT) award from the Ministry of Education, Government of Pakistan, which enabled him to pursue postgraduate studies in the United Kingdom. He completed his MSc in medical physics from the University of Surrey, Guildford in 1991. And achieved a significant academic milestone by earning a PhD in medical physics from King's College London, University of London in 1996. Professor Syed's journey from a modest village school to renowned UK universities is a remarkable testament to his determination and scholarly excellence. His strong academic foundation and passion for science have shaped a distinguished career dedicated to education, research, and healthcare innovation. Upon returning to Pakistan, he played a pioneering role in developing the field of medical physics at the University of Sindh. His efforts were instrumental in establishing and enhancing both undergraduate and postgraduate programs. In recognition of his academic leadership and research contributions, he was promoted to associate professor in 1999 and to full professor in 2004. Seeking broader international engagement, he joined the School of Health Sciences at University Sains Malaysia from 2001 to 2004. During this tenure, he was honored with the Best Lecturer Award and secured a competitive research grant, achievements that deepened his global academic perspective and research capabilities. Professor Syed is widely recognized for his impactful and innovative research. He has published extensively in reputed national and international journals and has co-authored 2 books on research methodologies. His work has been honored with numerous accolades, including gold, silver, and bronze medals from prestigious exhibitions such as IRAE, ITX, INEX, and MT. His research excellence is further evidenced by a granted patent and a portfolio of completed and ongoing projects. Since July 2009, Professor Syed has been serving as a faculty member in the Department of Diagnostic Imaging and Radiotherapy, Kulliyah of Allied Health Sciences, International Islamic University Malaysia, IIUM. His ongoing commitment to academic excellence, research innovation, and international collaboration continues to advance the field of medical physics and medical imaging, making a lasting impact on healthcare and higher education. Aside from being an excellent academician and researcher, Professor Syed is also a devoted and lovable father. His warmth, kindness, and unwavering support for his family reflect the same dedication and compassion he brings to his students and colleagues. His nurturing personality has inspired many not only in academia but also in life. As we celebrate his journey, We honor not only his remarkable achievements but also the profound influence he has had as a mentor, leader, and role model. Thank you, Professor Syed, for your unwavering dedication and the lasting impact you have made on countless lives.
Assalamu alaikum, Baba, congratulations on this big day. I'm so excited and so happy, and we are all truly proud of you. We have heard your stories from childhood and how you've come from a humble background and grown up so much. That has been truly inspiring, and the fact that you make us part of everything, be it, like reviewing your research papers, being there. So we've all seen you grow, we've been part of it, and I'm truly proud of you. We all are. And although I'm not there physically, but I'm still there, and I joined virtually, so it was very heartwarming to have this. And in our hearts, you're always a professor. Even before joining IIUM, you're always a professor. So yes, congratulations.
Such a beautiful and inspiring tribute. I would now like to invite Professor Dr. Syed Inayatullah Shah, accompanied by Dr. Iqbal bin Jamaluddin, Head, Department of Diagnostic Imaging and Radiotherapy, to the side of the stage for souvenir presentation. I now call upon Professor Dr. Samsul bin Rahman, member of the IIUM Board of Governors, accompanied by Professor Dr. Ahmad Aidil Arafat, to present a token of appreciation on behalf of the International Islamic University Malaysia. Thank you, Professor Dr. Samsul. You may kindly return to your seat. Professor Dr. Aidil, please remain standing. Next, I would like to invite Professor Dr. Ahmad Aidil Arafat on behalf of the Kulliyah of Allied Health Sciences to present a token of appreciation. Thank you, Professor Dr. Ahmad Aidil Arafat. You may kindly return to your seat. Next, I would like to invite Assistant Professor Dr. Aidi Aswadi bin Halim Lim, Head, Department of Radiology, Sultan Ahmad Shah Medical Center, IIUM, to present a token of appreciation. Thank you, Dr. Aidi Aswadi. Now, I would like to invite Assistant Professor Dr. Nur Ain binti Rabai from Department of Radiology, Sultan Ahmad Shah Medical Center, IIUM, to present a token of appreciation. Thank you, Dr. Nur Ain and Dr. Iqbal. You may kindly return to your seats. I would now like to invite Professor Dr. Syed's beloved wife, Mrs. Rabi'ah Shah Syed, to come forward and present a very special gift. Please welcome. And last but not least, please kindly welcome the rest of Professor Dr. Syed's beloved family to join him with love and appreciation. Son, Mr. Bilal Shah Syed. Daughter-in-law, Mrs. Farah Amirah Abdul Razak. Son, Mr. Suhaib Shah Syed. Daughter, Ms. Zuha Shah Syed. And not forgetting, Ms. Hajra Shah Syed, who is joining us virtually on YouTube. Let us give the entire family a warm round of applause. What a beautiful family moment. To add a sweet touch, we'd now like to invite representatives from the Department of Diagnostic Imaging and Radiotherapy to present a specially dedicated cake to Professor Dr. Syed and his lovely family for the cake cutting ceremony. Please welcome. Thank you very much, Dr. Iqbal, Professor Dr. Syed and his family. You may all kindly return to your seats. We will be moving on to the group photo session. For that, we would like to get your assistance to stand up and move closer to the stage. The VIPs can remain seated. The audience, please kindly stand up and move behind the VIPs. The photographer is going to be on the stage. Yeah. Please move closer. Please move closer. Okay. Please do not go back yet. We haven't finished. Let's just move closer. Thank you very much. Please kindly return to your seats. I would like to inform the YouTube live will end in a short while. Thank you to all the viewers who tuned in. We also kindly request all viewers to click the link in the chat box to fill in the evaluation form. Thank you. Please kindly return to your seats. We haven't finished.